All right. I want to move this a little bit the center. All right. All others you may be able to read, but I want to point out something important to you. This slide tells you the history of data models. What is a model, by the way, in general?
Model is like a category or
Yes, yeah, some of the, if you are making clothes, then you have a pattern, right?
yeah.
It's like that. When you have a machine learning, then you need to first find out a model. Once you have a model, then similar the instances can be applied to that models. Similarly, here database. When you design a database, then there may be somehow some architecture already designed. Some of the patterns are already defined. We call that models. So you can bring your data to fit in that models. So what kind of database models are available? So this slide tells you in early 1960s or even before, then we have file systems. And then little after that, hierarchical and network models. Hierarchical and network models are not really efficient to hold massive data sets, although it is a good idea. Therefore, in these days, that models were revisited when it comes to NoSQL databases or freestyle databases like web databases. In mid 1970s, then we have relational models, which is a first rigid data model. Once data is formed based upon relational model, then data can be maintained very efficiently and effectively, and in rigid manipulation. Therefore, database can be consistent. One of the important the feature of a database is the consistencies. If your database lose consistencies, then no one wants to use that database. For example, banking systems. You have your financial accounts at a bank. If a bank sometimes says, "Oh, your outstanding balance is $500," and next morning, "Oh, I'm sorry, my mistake. Your balance is $300," and then following morning, "Oh, another mistake." Then no one wants to use that kind of banking systems, right? Consistency is very, very important. So consistency has been maintained rigidly, consistently, effectively when it comes to relational models. So all the technologies have been developed rapidly, and therefore data can be consistently maintained and manipulated right now. For example, all your payroll systems, that is consistent. Your airline systems, of course, it is consistent. Hotel information, or your transcript systems, they are all consistent. Otherwise,
education system also.
which one?
Education system.
Education systems. you name it, right? All the systems maintain the data correctly, okay? Relational database works very well. Particularly, it has a very good language, so-called SQL. So we're going to use SQL a lot in this semester. This course conveys not only the database itself, but it conveys the security issues. So how can we add the values, more values, into small DBMS, so-called MySQL. MySQL is a good database management system, but it's not really strong enough like many other commercial DBMSs. Oracle, for example. You guys have heard of Oracle, right? But this guy does not. In this class, we're going to add some values into MySQL, although MySQL does not support you. But we know how to the code in Python, so we can add some values into MySQL. Therefore, MySQL will become a little more powerful in terms of security management. Okay, so we will do that. One of the good features of relational model is we can represent the data very, very efficiently. In this case, we can start with the conceptual modeling. We can analyze the real world domain and model it conceptually first, using ER diagram, entity relationship diagram. And then we need to convert that to relations. Relations in relational database is nothing but table. Relations is not the same as relationship. Relationship is the term used in ER diagram in this conceptual design. Conversion from conceptual design to logical design, relations or tables is called the relational design. We will see that a little later. This is 1970s. And mid-1980s, the researchers are thinking of object-oriented model. Around this time, object-oriented paradigm has been invented. Originally from MIT, early 1980s, and they are trying to adapt it to the coding and databases. They started thinking of the 1980s, mid-1980s. A lot of arguments, a lot of discussions had been going on for about 10 years. And after that, for example, in 1995, the first programming languages developed using object orientation, which is called Java. 1995. It took 10 years to make that happens. And then there is a coding communities. This object-oriented paradigm also implemented in database systems. We call that object-oriented databases. It has been developed in both here in America and also Europe, particularly in France. So they developed one, the DBMS, that runs on object orientations. Similarly here in America as well. But it has some drawbacks when it comes to object-oriented models. So it was not really widely used. Rather, up to this point, we had a relational model which is commercially successfully accomplished. Object-oriented model brings up very, very good ideas of representing complicated real world. Relational models does not cover all complexity of real world examples, but object-oriented models, it can cover all possible complexities in the real world. But it has a drawback. Drawback is the idea is not simple enough to implement. Implementation issue, and also language issue. In order to access data, then we need to use simple languages like SQL. But object-oriented model has very complicated languages involved. Therefore, it was not successfully implemented, although it has some good features. So we have good features here in relational models, which is SQL. We have good features here in object-oriented model, which is complex data types to be implemented. Next idea for this data model is how can we combine the strength from both data models, so that we made another ones called object relational models. So first object comes from object-oriented models. Relational comes from relational models. So looks nice idea, right? So they started in 1990s and implemented it. So current Oracle covers the great features of object relational data models, but we're not going to work on that. And after that, XML models, no SQL models, and more comes. But they're all simply the ideas, right? If data model is not rigid, then more coding efforts are required. If database management system gives you more strong features, then you don't really need to do much coding. Simply use it. It's always the trade-offs, right? For example, NoSQL data models. So data model itself may be simple, but in order to do all that strong features of database management, then everything is up to you guys. You have to code. So we're thinking of, in this case, in this slide, the college database or university database, student, course, transcript, faculty, etc. Okay. So we're thinking of, if it is a hierarchical structure, then the model becomes like this. Hierarchies, right? We have, for example, course ID, course title, and course description. And underneath, we have a class ID and meeting date and meeting location. And there are another sub concept. For that class, we have a department name and whatever about department. And also for that course, we have students, student ID, student name, and major. It's not really ideally designed in this way, but this is a way of designing the college databases in hierarchical models. This is hierarchical models. Network models, look at this simple example. Then we have some of the connections between entities. Let's say we have a department, faculty, student, and class. Then department and faculty, they are somehow connected. And faculty and class are connected. Class and students are connected. Students and department are connected. Somehow networks connected among those entities. That is network data models. As I said, in the mid-1970s, the idea of relational models has been invented by Card when he was in IBM, and it became it took a lot of attentions from data developers. So relational database management system commercially invented and commercialized. One of successful and available up to this point, the products is Oracle. And one small product is MySQL. So we are working on MySQL. Simple concept for relational models. Relational models has a table. We call that relations. Table has columns and rows. If it is a relational database, then it has multiple tables designed in it. So among those tables, among those relations, there may be somehow connections. Okay, they share. How do they connect from one relation to another relation? They can be connected by sharing a common entity characteristics. In other words, common attributes. In other words, common fields. As I said, relation is nothing but a table. It has columns and rows. So there may be common column. Consider two tables, two separate independent tables, like a class and students. Class and students. Students takes class. Students can be enrolled in multiple classes. But our design comes from the entities. What's available? What's available there is student, that is one entity. Class, there is another entity. There may be some actions when students register a class. How can we represent that? Student and class, there is no interactions. That's independent. In order to make them connect, then we need to share some of the common fields. I want to take a student ID from student. I want to take class CRN number from classes. Make one separate tables. So through that table, student and class can be connected, not directly but indirectly. indirectly means through that third tables. Some other cases, we don't need to even generate that third table. We simply share common attribute. For example, we have a department and students. Department and students independent, right? But when you join the college, then you can be in a specific department. Department has its own columns. Students has its own columns. If we want to connect them, then we need to share a column. Which column that we want to share? For example, department ID, cybersecurity. That can appear in student entity as a new name called major. So student has a major, cyber, that is the common,
between all the fields.
so common field with the department ID, cyber. In this case, they don't need to create third tables. Simply share from one field to another field. Send this field to another entities, therefore they are connected. So we have two ways, right? One way, we need to create separate tables, and both entities send their one of their column name into it. Therefore, third table can be constituted based upon the fields coming from both sides, right? There's one way. Another way is that we don't need to create third tables. Only send one of my column to you. So you can have my column, so that when it comes to your major, then through that major, then we know the department chair's contact information where Lola is majoring, right? Lola does not have department chair's phone number. Lola has a Lola own information. But in this relational database, because Lola has department send one of a field name to Lola, so Lola holds that common entity characteristics. Therefore, eventually, originally independent two entities, but by sharing that common attribute, they are connected. That is the idea of relational databases. It's a very good idea, right?
Okay.
Because the relational database is nothing but a collection of tables. Table is columns and rows. There's no way that we can, two different tables can be connected. But it can be connected by sharing common fields. Common fields may appearing in one table or may appearing in third tables, right? One from another, or common field from both sides to the third tables.
Can I go to the restroom 1 minute?
No?
No.
Why are you asking me? What if I say no? Okay, entity relationship models. So all these things, the idea is simple. Then when it comes to real big and complex application domain, complicated application domain, then it is not that simple, right? And also, so many people needs to be involved in analyzing the real-world applications. A lot of data, maybe it transferred from one entity to another entities. We need to identify, we need to define the entities, how many entities that we have. So many difficulties. I mean, so much. Therefore, we need to have somehow one solid models. That models, first of all, good to represent the real world information. We call that ER models. E from entity, R model relationship, ER models. It was introduced by Peter Chen in 1976 when he was in Harvard University. He's from Taiwan. He's a very short guy. I met him. He's now in Carnegie Mellon University.
Teaching as a professor?
Huh?
Is it teaching as a professor?
I think he's almost retired. He's very old, over 80 years old, but he's still associated with Carnegie Mellon. But before he joined the Carnegie Mellon, he was in Louisiana State University. But ER model, entity relationship models, so-called. Entity instance is a row in table. Entity set is a collection of like entities. So we have entity sets, we have a relationship set, object-oriented models, Okay, I want to skip this. Why don't I have the other relational models about this? Okay, here, therefore I have I need to have okay. So in this ER model, conceptual design using ER model about college databases. Then I want to bring another. Okay, I want to bring that. They should be like this. Okay, so it'll be like this. This is ER diagram. ER model, the result of ER model is ERD. So I would say here, entity relationship diagram. So entity relationship diagram consists of box, diamond, box for the entity sets, diamond for relationship set, and of course there are connections, right, among those. So and then maybe circle, we call that attribute. Something like this. Okay. So through the EL diagram, then we will have this kind of result. So we have a department. This is an entity set. What do you mean by entity set? Entity set is for example, entity set means a set of entity. Relationship set, same thing. Let's say we have a department. Then department has math department, computer science department, cybersecurity department, English department. So lots of departments, right? If we see the instances, the modeling means we are not talking about each individual objects. When we design models, then we need to, how can we make it conceptually simplify it? So collection of entity sets can be represented by one box. We call it department. We call that entity set. Entity set called the department is represented in this diagram as a box, but this box represents multiple objects of departments. Same thing, faculty, then they maybe Dr. Yoon, Dr. Smith, so many different faculty members. We collect them all and represent it in one box called the faculty. We call that entity set. Affiliates, there's a relationship set. So let's see. Okay, luckily I have this. So department has here department 1 and department 2. There's a set. Faculty has faculty 1, faculty 2, faculty 3. Faculty 1 has a relationship with department 1. Faculty 2 does not have a relationship. Faculty 3 has a relationship with the department 2. That may be, that kind of relationships possible if we take closer inside of that entity sets, right? Because the entity set is a collection of entities. So relationship is not between set to set. Relationship comes from element in that set. So one element in one set is related to another element in another set. by collecting those all element, by collecting those all relationships, we call that relationship set. That is another set, okay? That relationship set is now represented in a diamond. Okay? Jamal, you want to ask a question?
No, not a question. I have idea. Maybe we can do it in the whiteboard.
I wish I could do that, but we have only 3 students here. 5 students, I'm not sure. I'm worrying about them. This is a in-person class. They do not come. So our courtesy is, I want to record this and provide them some of the recordings. If we have some cameras that represent me, then I can draw on this whiteboard. It's much easier, right? Much easier. But conceptually, you understand what I mean by that, right? So relationship set. So there are a lot of things in theory are developed. For example, participations. All the entities in one entity sets should participate in the relationship sets, or partially. For example, here, the right-hand side, not all the elements in faculty are participated in this affiliation relationship set, right?
Yeah.
This is partial participation. If we see here department, then there's a total participation, something like that. That kind of theoretic analysis has been done by researchers, but anyway, we do not need to worry about that. It's all such details, right? Same thing here, department and major. So department has a lot of departments there. Students has lots of students. So some students may major one specific departments. Same thing here. Also, department. Let's say here we have students. Then we have student 1 and student 2 and student 3 and student 4 and student 1 may be major D1, student 2 may be major D1, student 3 may be major D2, student 4 now stop, right? That kind of things may be the real world situation. That real world situation may be represented in this way, conceptually. So department, major, and student, right? Same thing here, class and students. I can represent it again. Here, the students, S1, S2, S3, S4. So we have that. And then class, maybe here, class 1 and class 2. Student 1 takes class 1 and class 2. Possible, right? Student 2 takes class 1 only. Student 3 takes class 2 only. That is also possible. Right? Then we need to, this is very, very important. In this case, student in any student in a student relations student entity sets can take more than one class, right? Because S1 takes two classes, S2 takes one class, S3 takes one class. But anyway, we can say any students can take at most more than one class, right? Same thing here. Each class here in this, in this entity set can have one or more students, right? Class C1 has 2 students, class C2 has 2 students, so more than 1 students. So in this case, the cardinality may say many to many. Okay, but how about this? Each student can measure one department, right? Each student can measure at most one student, one department only. So we call 1. In this case, many to 1. Why many here? Each department has at most many students. Department 1 has 2 students. Department 2 has 1 student. So in this case, cardinality is many to 1. Can you see the difference? Here, many to 1 here, and many to many here. Same thing here. Department and faculty. Then a department may contain at most many faculties. So many faculties. Each department should be associated at most one department. Then in this case, 1 to many. That's a little bit of theory. Cardinality. I want to make this, oh no. Keep, then I want to see here. They may be I call that mapping cardinality. In each relationship set, there may be a mapping cardinality defined. This cardinality is very, very important when it comes to logical design. Logical design means this like this, and before I forget, I need to because I saved this. Okay. So ER diagram, basic structure that we looked at. Okay, after this, then we need to do logical design is. Logical design is nothing but converting the conceptual design, converting that means from ER diagram to relation schema. Relation schema is a collection of table description. Table description is a pair of attribute name and type. So relation schema is nothing but a collection of, roughly speaking, it is nothing but an attribute, collection of attributes. So what is a logical design? Logical design is, so outcome of a logical design is relation schema. Outcome of logical design is relation schema. What that means is that outcome of logical design is a collection of attributes. Okay. So again, this I want to think of this and that together. So for example, this is ER diagram, right? So from department we have department ID and chair and those information, maybe. relation schema from department we have a collection set of attributes that may be generated. From faculty, we have faculty ID, faculty name, and degree, for example. Right? So we are thinking of this department and faculty. What about this relationship? Remember that relationship? Maybe this department and faculty may not, they are independent entity set originally, but they may be connected through this diamond. How can they be related? They can be related by sharing common attributes. In order to make them department and faculty, as you see here, from that logical design, we have only set of attributes for department and set of attributes for the faculty. To represent this diamond, then we need to share. So which one can be shared? DID here or FID over here? If I have FID over here or DID, one or the other, which one is good, which one is no good? Let's consider this first, FID over there. I want to think of real table. If you see the real table, okay, this is real table. This is department table. So DID, chair, FID. DID cyber. Chair, let's say Yoon. FID, how many faculties? Chen, Uzman. Is it possible? Right now we have here comma. What do you mean by that? It's not really value. It should be one value. Why do we have that the set values? Set value is not allowed. There's a problem, right? On the other hand, if we do similarly, let's say FID here, name, degree, and then we can insert one more here, and then say DID. Let's say Yoon, no, faculty ID, 01, Yoon, department ID, department cyber, let's say 02, Chen, department cyber, 03, Uzman. Very nicely can be fit in, right? This, we have the problem. So which one is right? Sorry. Right? So we cover this. This ER diagram, department, diamond, faculty, that can be converted into this. This is called relation schema. So we have a relation schema. We have more, right? Now we need to do here department and students. Let's say student. Student has student ID, CWID, and student name. Okay? Let's say student's phone number. Students is related with the department, like major. So what should we do? Like a department here, we need to share, to represent this, we need to share the common attribute, right? Are we going to make a common CWID here? Or department ID here, we call that major. Which one is correct? Which one is wrong? We need to make a major over there, right? If we have a CWID, then we have the same problem that we had, right? Bigger problem. Department has how many? Cybersecurity, we have 100, almost 200 the students. Are we going to list all the 200 students in that row? No. Very nicely, so we can say major is nothing but DID over there. And we call that, hey, DID is a primary key. This is a foreign key, for example, right? So this is by on the line, we call that. Primary key, and CWID, that is also primary key. Primary can be represented in this relation schema. But this foreign key, we need to say somehow, right? Major is nothing but DID here. So this is a foreign key. DID here, that is also foreign key, namely the same as DID here, department. This is like a logical design. I'm doing this very quickly, because this is a graduate course. We don't. Conceptual design itself, some classes, it takes 1 week or 2 weeks. But with conceptual design, we don't spend much time, right? But you can generate this kind of ER diagrams by considering, if you know some application domain, application problems clearly well, then you can generate that kind of ER diagram, right? Diagram can be generated with no big problem.
Come on, man. Yeah,
But anyway, and then given that ER diagram, I'm talking about some of the procedures. So given application domain, like payroll systems, or banking systems, or airline systems, whatever that you think, right? Then you need to first understand all data flows, all the attributes of that. You need to first define entity sets. Which entity set you need to consider? Like here in the university database, then university where there are students first of all, and faculty, and department, and class. Right? So those 4 items are represented here in a box. We call that entity set. And then we can think, is there any relationships between the 2 or among 3 or whatever? It could be not only binary relationships, but maybe ternary or tertiary or 3 or 4, 2 or 3, 2 or more entity sets can be involved in one relationship set. That is also possible. So class also same thing here. Class has class ID, CRN, and title, class title, and credit, number of credits. Let's say student, we covered the students, and class, yes, here. What about this enroll? Enroll, by sharing common attributes, we can make some of enroll, right? But when it come here, let me go back to the previous slide. Department and faculty, we have a one-to-many relationships. Department and students, we have a many-to-one relationships. Department, student and class, we have a many-to-many. If we have a many-to-many, then in the logical design, it is not, in this case, do we need to share? For example, class CRN number in here or CWID here? Which one is better? Or both are the problem? Student, CRN. Ruth takes 3 courses. It's not one atomic value here, CRN, right? IASP 505, IASP 530, IASP 525. Is that right? That is the same problem that we had. Something comma, another comma, another comma. It's not atomic values. That is a problem. What about here, CWID? Class has, for example, IASP 525, title, distributed database and security, credit, 3 credit hours, CWID. 8 students. So, one or the other, so far, up to these points, one or the other may be okay, but in this case, not okay, both of those. Therefore, what happens? Enroll, this relationship can be a separate third table, and then we bring this CRN from there, here, and CWID here, not there, but like this. So when we had here many-to-many, like this, then we need to have a new table, right? So I would, I would highlight this, right? It's a newly generated table. That table is generated in the process of a logical design. In the conversion from conceptual model to relation schema. Finally, class and faculty. We have teach. Class we already had here. Faculty we have here, class we have there. What about teach? If we say one faculty can teach at most 2 or 3 classes, a class can be taught by at most 1 faculty, then that is a one-to-many relationship. If it is a one-to-many relationship, like here, then we don't need to create new table, but we need to share common attributes. Should the faculty share the class information, or class should share faculty information? Let's try to do that. Okay, between faculty and class. CRN here, or faculty, FID here, or we can say instructor. If a faculty can teach more than 1 courses, then we have CRN, multiple CRNs, right? If class should be taught by at most 1 instructor, then this is 1 value. Should come here. This is okay, but this is not okay. So we need to remove that. Right? Very nicely we made. So this is complete. This is a complete outcome from that logical design. Any questions so far?
I took SQL with you in the first semester.
Right, that's 505, right?
Yeah, the
But-
fundamental of cybersecurity.
Right,
Yes.
but there we don't cover this. We skipped it. Right now, Ruth knows that.
Well,
Yeah.
I like it because it's like a challenge. I remember I built a
Mhm.
very complex database as a practice.
Mhm.
So I like the topic.
So in this way, if we have a very complicated ER diagrams, multiple boxes and diamonds, and all kinds of things, you can convert that to real relation schema. Once you have this, then you can open up MySQL and design it, right?
Yeah.
Ruth knows how to create tables. I know Lola and Jamal, you forgot, right? You forgot. But next week we'll refresh it.
I have a question. Which better, Microsoft Access or SQL for database?
Microsoft Access is not a database.
It's an application for database.
It's just toy.
The
MySQL is kind of DBMS, but still it's not powerful. But MySQL is a DBMS. Access in Microsoft, that is the toy.
Yeah,
Yeah, toy. So we are now ready to do MySQL, but If we open up MySQL, then it takes another 3 hours. So,
Another class.
so this design stop here, and then, but I'm going to complete this slide very quickly. And after that, we are ready to do relational database, right? Now, object-oriented models, object-oriented model. If we do it in object-oriented models, then I am going to back to the example. I am going to bring it here. Not relational schema, but now we need to think of object-oriented schema. Department has chair that, and we don't need to do this. We don't have in object orientation, we do not have that primary key. We simply have I think we need to do this way. Department has DID is integer, DID is text type. Chair has text type. FID, faculty ID is integer. We're talking about the type of that data. Name, that is also text. Degree, that is also text. And we call here affiliation. Type of affiliation is department. Student's CWID is integer. Type of name is text. Type of phone number is integer. And major is type of major is department. I want you to compare these two. This is a relational database schema there. Type of DID is there's text. Chair, that is text. FID integer. Name text. Degree text. In relational models. DID, that is text. I want you to see the difference. Here DID is a text. Affiliation is department. Do you see the difference? Same thing here. CWID, type of CWID integer. Type of name is text. Type of phone number is integer. Type of major, there's nothing but department ID, so that should be text. But major here, there's a department as well. Class CRN integer. Title text. Credit integer. Instructor text, like here FID, instructor is integer because this integer should be the same as FID here, instructor, right? But here in this case, CRN is integer. Similarly, text title is text. Credit is integer. Instructor is type of instructor, faculty. These are the difference. CRN here, integer. CWID, integer. Here enroll, CRN is class. Type of CRN is class. Type of CWID is a student. What is the issue here? The issue here, each relation defined each relation or table that is defined can be a type of the data object set. This is department table. There can be a type, department. Faculty can be a type. Students can be a type. Class can be a type. That is what object-oriented and object relational data model can provide. Make sense? That is exactly the same as in object-oriented coding, programming, object-oriented languages, Java, Python, whatever object-oriented programming languages. If you define a class, it can be a type. Question so far? What else? Unstructured data models. So there are unstructured data models also possible. XML, NoSQL, those other things. Physical models, storage structure. So we have a conceptual model, logical models, and physical models needs to be considered as well. What that means is that how efficiently we want to store the data in a file. Depending upon that, retrieval time can be determined. Availability and efficiencies. So file organizations. In databases, file organizations in three ways: sequential, indexed, and hashed. Sequential, if you don't do anything, then there's a sequentially stored. And indexed and hashed. File organizations is another factor for selecting to determine throughputs, retrieval times, how fast data can be retrieved, how efficiently data is stored in a file. Protections. Data can be encrypted. Therefore, although your file is hacked by attacker, data is compromised, but attacker cannot recognize the data if it is encrypted, or it takes time to decrypt. Minimizing need of reorganizing, accommodating the growth, scalability, that is also a big issue, and security. Therefore, sequential files are maybe simple sortings, or not even sortings. So if it's not sorted, then it takes randomly. If it is sorted, then sorted files, then depending upon the search, we can improve a little bit if we know binary search. Then your coding is involved in this case, because the data itself not really organized the way that you can simply access. Simply, it is stored sequentially, in sorted way. if we want to improve the search condition, then you can implement it, the binary search mechanisms in your codings. Index file is very, very common. For example, student tables. Sometimes we can access student by student ID, right? But some other times we can access students by major. I want to retrieve cyber majors. Or some other times we can access it by GPA. So given one table, we may create multiple index files, 0 or more index files. For student table, we can have an index by CWID, index by GPA, index by major, index by country code, index by address, so many things, right? One of the typical index is like tree structures. But you guys didn't take yet any data structures course. Maybe Ruth, did you take data structures in your undergrads?
I took it
Data structures?
No.
Okay. Then you can think of this data structures, a tree structure, but this is a B tree. Each node has the value, index value, followed by pointer to child node. For example, F and P. Any value between F and P can be found if you go this link. That is the issue, right? Anything between P and Z, if you go to this link, then you can find. I think in this case, not really that. Anything smaller than F goes here. Anything between F and P goes here. Anything greater than P then goes here. In this specific example, but not. It depends on your implementation. Usually, not in this case, but usually we could have one more pointer here. Anything below F can be found here in this sub node. Anything between F and P goes here. Anything between P and G goes there. Anything greater than G then goes here. That is a typical. This is something awkward. But anyway, the idea remains the same. So that is a B tree or B plus tree, so-called, or B plus tree. B doesn't mean that binary. B means balanced. There are lots of true-false type of questions. B tree is binary tree. Yes or no? No. B tree means balanced tree. What do you mean by balanced? Depth is balanced. Whichever this or that, any value that you want to access, it takes the same time.
Same level.
Yeah. Depth remains the same. All is uniformly same. That's the beauty of this B tree and B plus trees. Hash. We have hash function, hash algorithms. So depending upon these hash functions, then we can directly access to the node. There's a hash. Usually, division remainder is used. For example, hash function of 5. Then anything can be divided by 5. The remainder 0 then goes, all the files remainder 0 then goes to this node. If it's 0, remainder 0. If a remainder 1 goes to this. It's a remainder 3 goes to here. Remainder 4 goes here. Remainder 5, there's no remainder 5, right? Remainder 2 here. Remainder 5 means there is a 0. 5 is divided by 5 divided by 5, remainder is 0. So this kind of hash algorithm used to generate the hash files. Database interface to the user. So how can you access databases, MySQL? In our case, we look at the command line. We type on the terminals. Host applications, which means coding. We'll do a little bit of those. Code in Python to access databases. If you do this, then there are lots of job openings available, job opportunities.
I was just Googling if I can take a certificate in MySQL, and they mentioned the Python.
Web services, same thing. If you can develop something in some other languages, and then user can use a web to access. Remote application using smartphone. If you take .555, another course that I am teaching, mobile technologies, then smartphones. Okay, this is the end of today's lecture. Any question? Okay, so next week we will do hands-on practice. So bring your laptop and get your MySQL ready. We'll do some.
Tomorrow I'm traveling to Florida for 4 days, 5 days. I'm not sure. Maybe I will extend. So I will not be able to come next
Next semester.
next class.